Every point of light in the night sky is a message from a past you can never visit. This is the profound mystery at the heart of the observable universe, the ultimate cosmic horizon that cages our vision. By the end of this journey, you will understand not just the staggering scale of a 46.5 billion light-year radius, but the fundamental forces of physics that built this boundary. We will unravel how light, time, and the stretching fabric of space itself conspire to create a limit to what we can see, and confront what might lie beyond that final veil. How does a finite speed of light create a bubble of reality centered on you? What ancient wall of primordial light defines the edge of time itself? The answers will stretch your understanding of reality to its breaking point. What do you believe exists beyond the edge of everything we know? That bubble of visibility is not the universe. This is the first and most vital principle to grasp. We call it the observable universe for a reason, a spherical region of space from which light has had enough time to travel to our eyes or our telescopes since the very beginning. Think of it as a cosmic event horizon, a boundary of information. Everything inside that sphere we can potentially see. Everything outside, its light simply has not arrived yet and may never will. This creates a profound and deeply personal reality. You are, right now, at the exact center of your own observable universe. The view from your window is unique to your position in space and time, a bubble of reality 14.7 billion years in the making, with you at its heart. But here is where intuition betrays us. If the universe is about 13.8 billion years old, and light travels at a fixed speed, you might assume the observable universe's radius is 13.8 billion light-years. That is the light travel distance, how far the photons have journeyed. Yet the most distant objects we see are not 13.8 billion light-years away. They are actually about 46.5 billion light-years distant. This staggering difference is the key to everything. It means space itself was not a static stage while the light traveled. It was stretching, expanding, carrying those distant galaxies away from us even as their ancient light raced toward us. The Comoving Distance accounts for this expansion, telling us where that galaxy is located today, not where it was when it emitted the light we are just now receiving. So the true scale of our visible cosmos is a bubble with a radius of 46.5 billion light-years, not because anything moved faster than light through space, but because the fabric of space between us grew. This foundational idea transforms the edge from a simple distance into a story written by the expansion of the universe itself. 300,000 kilometers per second feels instantaneous on Earth, but across the cosmic ocean, it is agonizingly slow. This ultimate speed limit, the constant we call the speed of light, is the fundamental rule that shapes our entire view of reality. It is the messenger that brings us news of distant worlds, but it is also the jailer that confines us to a single, stubborn truth. We can only see what the light has had time to deliver. Every observation is therefore a delayed broadcast, a message from the past. That brilliant star you see on a clear night might have shone its light during the height of the Byzantine Empire. A galaxy glimpsed through a telescope may have emitted that photon when Earth's first complex life was just beginning to crawl from the seas. This is the principle of look-back time, and it turns the night sky into the most magnificent history book imaginable. We are not seeing the universe as it is, but as it was in 1,000 different eras all at once. The deeper we look, the further back in time we peer. This creates a layered fossil record of cosmic evolution. The most distant galaxies appear not as the majestic spirals we see nearby, but as blobby, chaotic nurseries caught in the act of formation. Their light is so ancient it shows us the universe in its youth. So when we point our most powerful telescopes at the edge of the observable universe, we are not looking across space in a simple sense. We are launching a probe directly into the deep past, using light itself as our time machine. But if light's finite speed creates this cosmic delay, what force is responsible for stretching the universe to that staggering 46.5 billion light-year radius? The answer lies not with the messenger, but with the stage upon which it travels. Edwin Hubble's discovery shattered a static, eternal cosmos forever. Peering through the Great Telescope at Mount Wilson in the 1920s, he made a simple but terrifying observation. The light from nearly every distant galaxy was stretched. Its wavelength shifted toward the red end of the spectrum. More startling still, the farther away a galaxy was, the greater this redshift became. The universe was not standing still. It was in motion, a grand and relentless retreat. The immediate, intuitive explanation was that galaxies were flying apart through space, like fragments from some ancient explosion. But the truth is far stranger, and it redefines the very meaning of distance. The galaxies are not primarily moving through space. Instead, the space between them is stretching. Think of the universe not as an empty box with galaxies inside, but as the surface of a balloon. Draw dots on that balloon to represent galaxies. Now inflate it. No single dot moves across the surface, yet every dot moves away from every other dot as the rubber stretches. The fabric itself is growing. This is the expansion of the universe. It means that light emitted from a distant galaxy is not just traveling across a fixed distance. It is embarking on a marathon where the finish line itself is constantly being moved farther away. The space between the photon and us is elongating during its entire multi-billion-year journey. This cosmic stretch has a direct, observable effect. It saps the energy of the traveling light, stretching its wavelength, causing that telltale redshift. It also explains the impossible scale of our visible cosmos. Because space expanded as the light traveled, the galaxy that sent that ancient photon is now vastly farther away than a simple calculation based on light travel time would suggest. That photon left its source 13.8 billion years ago, but it has been fighting against an expanding track the entire way. By the time it finally reaches our telescopes, its point of origin is not 13.8 billion light-years distant. It is a staggering 46.5 billion light-years away. The expansion of space did not just create more distance, it created more time for that light to travel, allowing our observable bubble to become far larger than the age of the universe might naively suggest. But if space itself is stretching, carrying galaxies apart, what is the source of this immense, relentless force? What engine drives the balloon to inflate? The journey of that ancient photon is a race against an expanding finish line. To understand how we arrive at that 46.5 billion light-year figure, we must follow its path, not through static space, but through a cosmos that is actively growing. Picture a single photon, a particle of light, emitted at the dawn of time from a hot, dense plasma that filled the entire universe. Its destination is us, but the very fabric it travels through is stretching. For every billion years that photon spends in flight, the distance it still has left to cover gets a little bit longer because the space ahead of it is inflating. It is like a marathon runner on a treadmill that is slowly accelerating, forcing them to run farther than the original length of the track just to reach the end. The light from the cosmic microwave background, that faint afterglow of the Big Bang, has been running this marathon for 13.8 billion years. But during all that time, the universe has been stretching, pushing its source farther and farther away from us. So the question cosmologists ask is not, how far has the light traveled? That is 13.8 billion light-years, the light travel distance. The real question is, where is the source of that light located today? To find that, we must account for every moment of expansion that happened during the photon's entire journey. We have to rewind the expansion of the universe mathematically, and calculate how much space has been added between that point of origin and us over cosmic history. This calculation gives us the Comoving Distance. It is the true present-day distance to the source of the oldest light we can see, factoring in the relentless growth of the cosmos. When we run the numbers using our best measurements of how fast the universe has expanded over time, that Comoving Distance comes out to approximately 46.5 billion light-years. That is the radius of our cosmic horizon. It means the most distant event we can possibly observe, the birth of the cosmos itself, is not 13.8 billion light-years away. Its echo comes from a place that is now almost 3.5 times farther, simply because the space in between has ballooned. So the edge of the observable universe is not a wall in space. It is a moment in time, the moment of first light, viewed from a location that has been carried to an unimaginable distance by the expansion of everything. But this raises a haunting new question. If the universe is 46.5 billion light-years wide in every direction from our vantage point, what does that imply about its total size, the size of the universe beyond what we can ever see? This faint glow is the oldest photograph ever taken. It is the cosmic microwave background, a whisper of radiation that fills every cubic centimeter of the void with a temperature just 2.7 degrees above absolute zero. To understand this signal is to reach the absolute limit of our vision, the final wall we cannot see past. For the first 380,000 years of cosmic history, the universe was an opaque, searing fog. It was a plasma so dense and hot that light could not travel freely. A photon would be emitted, only to be immediately swallowed again by a free electron, trapped in a chaotic dance of creation and destruction. The cosmos was a brilliant, blinding prison of light. Then, in a pivotal moment, expansion cooled the universe enough for a fundamental change. Electrons finally combined with protons to form the first stable atoms, mostly hydrogen. This event, known as recombination, suddenly cleared the fog. With the electrons now bound into atoms, the photons that had been trapped were set free, streaming outward in every direction. That first burst of liberated light, after a journey stretched by 13.8 billion years of cosmic expansion, is what we detect today as the cosmic microwave background. It is not light from a star or a galaxy. It is the afterglow of the universe's fiery birth, cooled and diluted by eons of expansion into a uniform microwave hum. When our radio telescopes map this signal, we are not looking at an object in space. We are looking directly at a moment in time. We are seeing the glowing surface of that early universe, a wall of primordial light that marks the horizon of optical astronomy. Every direction we look, this wall is there, a fossilized shell that encapsulates us completely. It is the baby picture of the cosmos, a snapshot of its infancy, and it defines the temporal edge of everything we can ever hope to observe with light. Beyond this wall lies the universe's true early childhood, a period forever hidden from our direct view, shrouded in that initial, impenetrable fog. That wall of light is not just a barrier, it is a revelation. It tells us the universe was once small enough, hot enough, and uniform enough to glow like the surface of a star. But it also marks the final curtain we can peer behind with light alone. To see beyond the cosmic microwave background is to try and look through a brick wall. For the first 380,000 years, the cosmos was not a transparent void. It was a searing, churning plasma, a thick soup of fundamental particles. Protons and electrons roamed freely, unbound, and light was their prisoner. A photon would be born in a collision, only to travel a minuscule distance before being violently absorbed and re-emitted by a free electron. This constant scattering meant light could not travel in a straight line or even a coherent path. The entire universe was an opaque, brilliant fog, glowing white-hot but impossible to see through. This epoch is our ultimate horizon. We call it the Era of Opacity, and it places a fundamental limit on our vision, a frontier built not by distance but by the very state of matter. The cosmic microwave background is the flash of light released the moment the fog cleared. It is the afterimage of that last scattering event, frozen in time and stretched across the sky. So when we map that microwave glow, we are not seeing past it. We are staring directly at its surface. The universe before that moment is shrouded, hidden behind the very conditions that made the early cosmos so energetic. This presents a profound challenge. How can we possibly understand a universe we cannot directly see? The answer lies not in telescopes, but in detective work. We must become cosmic forensic scientists. While we cannot receive light from the opaque era, the universe left clues imprinted on the very light that escaped. The patterns in the cosmic microwave background, those tiny temperature fluctuations that look like static on an old television, are not random noise. They are a fossilized imprint of the density ripples that existed in the primordial plasma. Those ripples were the seeds sown by physics in the first fraction of a second after the Big Bang, and they grew under the force of gravity during the opaque era. By studying the precise statistical patterns of this cosmic fingerprint, we can work backwards. We can deduce the conditions of the soup, infer its composition, and test our theories about the forces at play in that first, invisible chapter. It is like studying the sound of a bell long after it has been rung. From the echo, we can deduce the bell's shape, its size, and what struck it, so the era of opacity is not a complete blank. It is a dark room we must illuminate with the echoes that finally escaped. This cosmic fingerprint holds a secret that nearly broke modern cosmology. When scientists first mapped the faint glow of the cosmic microwave background with exquisite precision, they expected to find a tapestry of variation, hot and cold spots telling the story of a chaotic young cosmos. Instead, they found something deeply unsettling, a uniformity so perfect it defied logic. The temperature of this ancient light is the same in every direction we look, to an astonishing precision of 1 part in 100,000. Whether we point our telescopes north, south, east, or west, that fossilized radiation reads 2.725 degrees above absolute zero, with only the tiniest of fluctuations. This presents a profound paradox known as the horizon problem. Think of it this way. The cosmic microwave background we see from one side of the sky comes from a region of the early universe that is now 46 billion light-years away in that direction. The light from the opposite side of the sky comes from a region 46 billion light-years away in the completely opposite direction. The total distance between these 2 points on the edge of our observable bubble is a staggering 92 billion light-years. Yet, this light was emitted when the universe was only 380,000 years old. At that tender age, even traveling at the speed of light, there simply has not been enough time for any signal, any influence to have traveled from one of these regions to the other. They were causally disconnected, forever out of each other's reach, like two islands separated by an ocean too vast to cross. According to the basic laws of physics, these isolated regions should have evolved independently, developing different temperatures and densities. They should be as different as 2 pots of water boiling separately on different stoves, yet they are identical to an almost impossible degree. It is as if you walked into 2 separate, soundproof rooms on opposite sides of the planet and found 2 pianos playing the exact same note at the exact same volume with no conductor and no communication. How could regions that never touched possibly agree on a single temperature? This paradox pointed to a glaring flaw in our understanding of the universe's earliest moments. The smoothness demanded an explanation, a mechanism that could have connected these distant horizons before the light we see was ever emitted. The solution would require us to rewrite the first chapter of cosmic history, introducing a moment of unimaginable violence that reshaped the very fabric of reality. To resolve this impossible uniformity, physicists proposed a moment of breathtaking violence in the universe's first instant. The theory of cosmic inflation suggests that a fraction of a second after the beginning, the universe did not simply expand. It exploded in scale at a rate that defies everyday intuition. For an unimaginably brief period, perhaps as short as 1/1,000,000,000 of a trillionth of a trillionth of a second, the fabric of space itself stretched faster than the speed of light. This idea does not break Einstein's rules, because relativity only forbids objects from moving through space faster than light. It places no limit on the stretching of space itself. Think of it as the difference between a fish swimming through water, bound by a maximum speed, and the water itself rapidly flooding a dry basin. The water level can rise faster than any fish could ever swim. Inflation was that cosmic flood. During this fleeting epoch, a region of space smaller than a single proton was stretched to a size larger than our entire observable universe today. This explosive growth smoothed out the cosmos like stretching a wrinkled rubber sheet until it becomes flat and featureless. It took any tiny variations that existed and diluted them to near perfection, explaining why the cosmic microwave background is so uniform. More importantly, it solved the horizon problem. Before inflation, all parts of that primordial, subatomic seed were in intimate contact, able to reach a common temperature. Then inflation violently pushed them apart, separating regions that were once neighbors by distances far greater than light could have traveled in the time since. What we see as causally disconnected points on opposite sides of the sky were once close enough to whisper to each other before being ripped apart by the stretching of space itself. But inflation did more than just smooth and flatten. It also planted the seeds for all future structure. Quantum fluctuations, those tiny, unavoidable jitters at the smallest scales, were stretched along with everything else. As space inflated, these microscopic ripples were blown up to cosmic proportions, becoming the slight density variations we see imprinted in the cosmic microwave background. These are the gravitational seeds around which, over billions of years, galaxies and clusters would eventually coalesce. Every galaxy, every star, every planet owes its existence to quantum whispers magnified by inflation into the architecture of the cosmos. This theory carries a staggering implication for the true scale of reality. If a region smaller than a proton could be inflated to a size larger than everything we can see, then what lies beyond our 46.5 billion light-year horizon? Inflation suggests our entire observable universe is just one smooth, flat patch within a vastly larger, and perhaps infinite, whole. We are confined to a single bubble within a cosmic froth, an island of visibility in an ocean of space that stretched far beyond the reach of any light that will ever reach us. The universe beyond our horizon may be endless, filled with other such bubbles, other cosmic domains with potentially different properties, forever separated from us by distances that grew insurmountable during that first, violent moment of creation. So the edge we have been searching for is not the edge of the universe. It is merely the edge of our local neighborhood, a horizon created by our own limited place in a much grander and likely infinite tapestry. This distinction between horizons reveals a deeper layer to our cosmic isolation. We have been exploring what we call the particle horizon, the absolute limit from which any particle, any bit of light or matter, could possibly have reached us since the beginning of time. It is a boundary set by the past, a map of everything we have ever been able to see. But in an accelerating universe, there exists a second, more haunting frontier, one that looks not to the past but to the far future. This is the cosmic event horizon. Think of the particle horizon as a wall behind us, marking the oldest light we will ever receive. The event horizon is a wall ahead of us, defining the newest light we will ever see. It is a future boundary created not by the age of the universe, but by its accelerating expansion. Because space is stretching at an ever-increasing rate, there comes a distance where the space between us and a distant galaxy is growing faster than light can cross it. A photon emitted from a galaxy beyond that critical distance today, no matter how powerfully it shines, is destined for a futile journey. It is like a swimmer trying to cross a river where the current is constantly accelerating. Even swimming at top speed, the far shore recedes faster than they can approach. That light will never, ever reach us. The galaxy that sent it has already passed beyond our ultimate reach, vanishing from our future. This means the observable universe is not a static bubble that simply grows with time. In an accelerating cosmos, it is a bubble that is actually shrinking in terms of the number of galaxies it will ever contain. As more and more regions of space cross that event horizon, they fade from view, their light stretched into undetectable infrared wavelengths and then into nothingness. For any future civilization looking out at the cosmos, the universe will appear progressively emptier and darker. Galaxies we see today will one by one slip over this cosmological horizon, their final photons arriving as an infinitely dim, redshifted farewell. The cosmic event horizon, therefore, paints a profoundly different picture of our place in the cosmos. The particle horizon tells us what we can know of the past. The event horizon dictates the limits of our future knowledge, a slow closing of the cosmic curtains driven by the relentless and silent acceleration of empty space itself. Light may be trapped, but the universe has another messenger. Gravitational waves are not ripples in water or vibrations in air. They are distortions in the fabric of space-time itself, generated when massive objects undergo violent acceleration. When two black holes spiral together and merge, they do not give off a flash of light you could see with your eyes. Instead, they send a shudder through the cosmos, a literal stretching and squeezing of the distances between everything. This wave travels outward at the speed of light, but with a crucial difference. It is not made of particles that can be scattered or absorbed. It is a warp in the geometry of reality, and it passes through the densest, most opaque matter as if it were not even there. Where the early universe was a blinding fog to light, it was nearly transparent to these tremors in space-time. This means gravitational waves carry information from eras forever hidden from our telescopes. They are a new sense, allowing us to hear the universe in a way we have never seen it. The first direct detection of these waves in 2015 was a monumental leap, confirming a century-old prediction by Einstein and opening an entirely new field of astronomy. But the signals we currently detect are like hearing the nearby crashes of modern cosmic events. The true potential lies in listening for the faintest whispers from the very beginning. Future observatories like the planned space-based mission called LISA, the Laser Interferometer Space Antenna, aim to do just that. By placing 3 spacecraft in a giant triangular formation millions of kilometers apart, it will detect the minute wobbles caused by passing gravitational waves. Its goal is to tune into the lowest frequencies, the deep hum of the most massive events in cosmic history. This could include the chorus of millions of merging supermassive black holes across the universe. But even more tantalizing is the prospect of hearing the echoes of the universe's birth. Certain theories suggest that the violent process of cosmic inflation, that moment of faster-than-light stretching, would have generated a background rumble of gravitational waves, a primordial signal imprinted on the fabric of space-time in the first trillionth of a second. Detecting this cosmic gravitational wave background would be like finding the fossilized vibration of creation itself. It would offer a direct glimpse into that unimaginably hot, dense, and opaque epoch, effectively allowing us to peer behind the curtain of the cosmic microwave background for the very first time. Where light stops, the ripples in space-time may carry the story forward, expanding our effective horizon not in distance, but in time, taking us closer to the moment of genesis than we ever dreamed possible. But the faint hum of gravitational waves is not the only whisper from the dawn. To push our vision even further back, we must listen for a ghost. The neutrino is arguably the most elusive fundamental particle in existence. It carries no electric charge, has almost no mass, and interacts with ordinary matter so rarely that it is essentially a phantom. A single neutrino can pass through a light year of solid lead without a single collision. This ghostly nature, while making them infamously difficult to catch, is also their greatest gift as cosmic messengers, for it means they can travel unscathed through environments that would instantly trap or scatter light. In the first furious second after the Big Bang, the universe was a dense, searing inferno where even the primordial plasma was opaque to photons, but for neutrinos it was nearly transparent. They decoupled from the rest of the cosmic soup a full second after the beginning, streaming freely into the expanding void while light remained imprisoned for another 380,000 years. This means a cosmic neutrino background must permeate all of space, a relic sea of these ancient particles even older than the cosmic microwave background. It is a fossilized snapshot of the universe at the tender age of 1 second, a time of incredible violence and transformation known as the epoch of nucleosynthesis, when the first atomic nuclei like helium and deuterium were forged in the heart of the newborn cosmos. Detecting this background is one of the most monumental challenges in all of physics. These relic neutrinos have been traveling for 13.8 billion years, their energy stretched and cooled by the expansion of the universe to a whisper above absolute zero. They are so feeble that they slip through our planet, our bodies, and our most sensitive detectors without a trace. Current technology is nowhere near sensitive enough to catch them directly. Yet the pursuit is a holy grail of cosmology. Success would not just be a new observation, it would be a leap across time. It would allow us to peer directly into that first second, to test our theories of how the fundamental forces behaved at energies far beyond anything we can recreate in particle colliders, and to understand the precise conditions that set the stage for the formation of every atom in our bodies. Where light gives us a picture of the universe at 380,000 years old, and gravitational waves may one day let us hear its first trillionth of a second, the cosmic neutrino background would offer a crucial, missing frame in between, a ghostly portrait of the cosmic infant taking its very first breath. The late 1990s delivered a shock that rewrote the destiny of the cosmos. Two independent teams of astronomers, painstakingly measuring the light from distant supernova, made an unsettling discovery. They expected to find that the expansion of the universe, set in motion by the Big Bang, was gradually slowing down under the relentless pull of gravity. The data told the opposite story. The expansion was not slowing, it was speeding up. Some unknown force was pushing the galaxies apart with ever-increasing vigor, a repulsive influence that overwhelmed the attractive grip of gravity on the largest scales. This mysterious driver was given a name that confesses our ignorance: dark energy. Its discovery was not just another entry in the catalogue of cosmic phenomena. It was a revelation that the universe's future is one of accelerating isolation, and it redefines the very nature of our horizon. Before this finding, cosmologists debated between two possible cosmic fates: a gradual slowdown leading to a static state, or a reversal into a catastrophic big crunch. Dark energy introduced a third, more haunting destiny: an eternal and accelerating expansion leading to what some call a cosmic heat death, a cold, dark, and empty eternity. This acceleration has a direct and calculable impact on what we can see. It ensures that the cosmic event horizon is not a distant, abstract concept. It is a real boundary, and it is surprisingly close. Based on our current measurements, this point of no return lies approximately 16 billion light-years away. Any galaxy beyond that distance today is already caught in a current of expanding space so swift that the light it emits now, at this very moment, is embarking on a futile journey. No matter how long it travels, the space between us and that photon is stretching faster than the photon can cross it. The galaxy has, for all practical purposes, already vanished from our future. It is a farewell we just have not received yet. This means dark energy is not a passive component of the cosmos. It is an active sculptor, shaping the future size and content of our observable universe in real time. As the acceleration continues, more and more galaxies will cross that 16 billion light-year threshold and slip beyond the event horizon. The universe for any future observer will not be a grand tapestry of billions of galaxies. It will be a local neighborhood, a lonely archipelago of a few gravitationally bound systems, surrounded by an infinite and ever-darkening void. The light from the receding galaxies will not simply dim. It will be stretched to wavelengths so long, so redshifted, that they become undetectable, fading from view entirely. Dark energy, therefore, imposes a finality to our cosmic view. It guarantees that vast regions of the universe, regions that exist right now, are and always will be fundamentally unknowable to us. We are not just limited by the past, by the time it has taken light to reach us. We are being actively cut off from the future by a force that ensures the cosmos will grow quiet, leaving us alone with the echoes of a receding past. Dark energy imposes a final, silent curtain on our future view, but inflation theory suggests our past may have been far more crowded than we ever realized. If that brief, violent moment of faster-than-light stretching did indeed happen, then our entire observable cosmos, that 46.5 billion light-year bubble, is likely just one smooth region within a vastly larger, perhaps infinite, landscape. This is the heart of the Multiverse Hypothesis, and it transforms the edge from a barrier of light into a border between realities. In an eternally inflating cosmos, the process that smoothed our local patch never truly stops everywhere. Think of it like a pot of water coming to a boil. Our universe is one single bubble that formed and stabilized, but outside our bubble, the inflationary energy still simmers, endlessly creating new space. In that seething, hyper-expanding background, quantum fluctuations can trigger the formation of other bubbles, other universes, each undergoing its own rapid inflation and cooling, each pinning down its own unique set of physical laws as it stabilizes. These bubble universes would be forever separate, expanding within a sea of inflating space that stretches faster than any signal could ever hope to cross. They are not stars in a shared sky. They are isolated cosmic domains, causally disconnected from the moment of their birth. So when we stare at the edge of our observable universe, at that wall of ancient light, we are not looking at the edge of everything. We are likely looking at the interior boundary of our local bubble. Beyond that wall of primordial photons lies not more of our universe, but the inflating void between bubbles, and then perhaps the membranes of other universes entirely. This idea moves the ultimate frontier from a question of astronomy to one of profound philosophy. What would these other realms be like? The constants that govern our reality are strangely fine-tuned for complexity. If the strength of gravity or the mass of an electron were even slightly different, atoms would not form, stars would not ignite, and life as we know it would be impossible. In a multiverse, this fine-tuning finds a possible, if speculative, explanation. In an infinite froth of bubbling universes, every possible combination of physical laws and constants will emerge somewhere. We simply find ourselves in one of the rare bubbles where the numbers allowed galaxies, planets, and observers to arise. We are not the center of a single, special creation. We are the inevitable product of a statistical lottery played across an infinite canvas. This challenges our very definition of reality and what is fundamentally knowable. A multiverse implies that the totality of existence is, by its very nature, untestable and unobservable from within any single bubble. The ultimate nature of things may lie permanently beyond the reach of science, confined to the realm of logical inference and mathematical elegance. So the journey to the edge of the observable universe ends not with a wall, but with a mirror. It reflects back our deepest questions about our own place in the cosmos. Are we alone in a single, vast but finite reality, or are we one voice in an infinite chorus of universes, forever separated by an unbridgeable sea of inflating space? The light from those other realms will never reach us, leaving the answer to echo only in the architecture of our theories and the quiet wonder of a star-filled sky. Our most powerful eyes are already straining against that ancient wall of light. The James Webb Space Telescope, with its gold-plated mirrors shielded from the sun, represents the pinnacle of our quest to see farther back in time. It does not look for the familiar shapes of modern galaxies, but for the faint, stretched infrared signatures of the very first star clusters to ignite in the cosmic dark. These are not the majestic spirals of today, but fragile, blobby assemblies of stars, seen as they were when the universe was a mere few 100 million years old. Each image it sends back is a deeper page in that cosmic history book, pushing our vision closer to the era of the first dawn. Yet even this technological marvel has a boundary it cannot cross, a limit written not by engineering, but by the laws of physics themselves. Webb operates by collecting electromagnetic radiation, the family of light that includes everything from radio waves to gamma rays. And all of that light, every single wavelength, was trapped in the opaque fog of the early universe until the moment of recombination. The cosmic microwave background is the final flash from that fog. No telescope, no matter how large or sensitive, can ever collect a single photon of starlight from a time before that wall formed. This is the absolute horizon for traditional astronomy. To see farther, we must not just build better telescopes, we must reinvent the very idea of observation. The next generation of observatories already on the drawing boards, like the Habitable Worlds Observatory designed to seek out Earth-like planets, or colossal ground-based telescopes with mirrors 30 meters across, will refine our view of the universe's adolescence in stunning detail. They may even capture the direct light of the first individual stars, monstrous behemoths that lived fast and died young. But they will all inevitably run into the same 380,000-year-old barrier. The opacity of the early universe is a fundamental curtain that electromagnetic radiation cannot part. So how do we look behind it? We must learn to listen and to feel. This is why the future of cosmology lies in detecting the universe's other messengers. Gravitational wave observatories like the planned space-based LISA array aim to tune into the ripples from the universe's first second. Neutrino detectors of unimaginable sensitivity may one day catch the ghostly sea of particles from that first fiery moment. These signals do not use light. They are carried by the fabric of space-time itself, or by particles that ignore ordinary matter. They offer a potential backstage pass to the earliest acts of the cosmic drama, eras forever dark to our eyes. Yet even these methods may have their own limits, frontiers defined by the energy of the early cosmos or the fundamental nature of the forces at play. To truly peer into the initial instance, to understand what sparked inflation or what, if anything, came before the Big Bang, we may need more than new instruments. We may need a revolution in physics itself, a new framework that can describe conditions of such extreme energy and density that our current theories of gravity and quantum mechanics simply break down. The quest to see farther is therefore a journey into the unknown on two fronts. It is a race of engineering to build detectors sensitive enough to catch the faintest whispers from the dawn. And it is a leap of imagination to conceive of the laws that governed reality when all of existence was smaller than a single atom. the ultimate telescope may not be a machine we build, but a theory we discover. This central position is not a cosmic accident, but a logical necessity. We stand at the heart of our own observable universe for the same reason you stand at the center of your own field of vision. Any observer anywhere in the cosmos will find themselves in the exact same situation. Look out from a planet orbiting a star in the Andromeda galaxy, and your night sky will be a completely different tapestry, with your own Milky Way as a distant smudge of light. You would be at the center of your own spherical bubble of visibility, bounded by your own particle horizon of 46.5 billion light-years. This is a direct and unavoidable consequence of two simple facts. Light has a finite speed, and the universe has a finite age. No signal, no information can have reached us from beyond the distance light has had time to travel since the beginning. So the sphere of what we can see is defined by our location in space and time. It is a personal reality, unique to our coordinates in the cosmos. This idea is deeply anchored in the cosmological principle, the bedrock assumption of modern cosmology, which states that on the largest scales, the universe is both isotropic and homogeneous. Isotropy means it looks the same in every direction. Homogeneity means it is roughly the same in every place. No single location is special. So if the universe is broadly uniform, then any observer, anywhere, will look out and see a cosmos that appears centered on them, surrounded by more distant regions whose light has not yet arrived. Our seemingly privileged central viewpoint is therefore an illusion of perspective, not a fact of architecture. It forces a profoundly humbling shift in thinking. We are not at the center of the universe. We are merely at the center of everything we can possibly know. This realization connects to a deeper philosophical idea known as the anthropic principle. In its simplest form, it suggests that the universe we observe must be compatible with the existence of observers like us. We could not find ourselves in a universe that prohibits life, because then we would not be here to ask the question. When applied to our cosmic horizon, it offers a quiet resolution to any feeling of loneliness or insignificance. Every conscious being that gazes at the stars anywhere is standing at the center of their own magnificent story, looking out at their own unique sphere of cosmic history. We all share the same condition of being anchored to a single point in an expanding sea of space-time, each of us surrounded by a personal horizon of light and time. The edge is not out there, it is woven into the very act of observation. The cosmos we see today is a temporary spectacle of unimaginable richness. That tapestry of billions of galaxies, each a city of stars, is not a permanent feature of the universe. It is a fleeting moment in cosmic time, a vibrant spring that will inevitably fade into a deep and silent winter. The very force that defines our current horizon, dark energy, is also scripting its slow demise. While our observable bubble remains a staggering 46.5 billion light-years wide, its future content is destined to wither away. The accelerating expansion of space acts like a cosmic tide, pulling islands of matter apart with ever-increasing speed. Most galaxies are not gravitationally tied to us. They are adrift on this tide, and as the space between us stretches faster and faster, a point of no return is crossed. Their light, struggling against an expanding track, becomes stretched to longer and longer wavelengths, shifting from visible blue to red into the infrared, and finally fading into undetectable radio waves. One by one, their final photons will arrive as an infinitely dim farewell, and then nothing. They will have passed beyond our cosmic event horizon, not by moving, but by the space between us growing insurmountable. For any civilization in our Milky Way galaxy gazing out in the distant future, perhaps trillions of years from now, the night sky will tell a lonely story. The grand spirals and brilliant clusters we take for granted will have vanished. The sky will be dark and nearly empty, save for the merged, aging stars of our own local galactic group, a few nearby islands that gravity has bound together against the tide. The universe will appear as a vast black ocean with only a single dim lighthouse. This is the ultimate implication of our shrinking future horizon. The accessible universe, the realm from which we can ever gather new information, will contract. We will be left with a fossilized record. The cosmic microwave background will still glow, a permanent monument to the hot beginning. The light from galaxies that crossed the horizon long ago will still be traveling to us, a museum exhibit of a more vibrant past. But the cosmos as a living, evolving entity, full of new events to witness, will have receded beyond our grasp. We will be archivists in a quiet library, studying the echoes of a cosmic symphony that has long since fallen silent. This future transforms our understanding of the present. We are living in a privileged era, a cosmic golden hour where the universe is still transparent, still full of light, and still telling its story. The edge we see is not static. It is a closing door, and we are fortunate enough to be here while it is still open. That faint, uniform glow is a masterpiece of cosmic cryptography. The cosmic microwave background, that wall of ancient light, is not perfectly smooth. When we map it with instruments of exquisite sensitivity, like the European Space Agency's Planck satellite, a breathtaking pattern emerges. The temperature of this afterglow varies by mere millionths of a degree, creating a mottled tapestry of slightly warmer and slightly cooler patches across the entire sky. These tiny anisotropies are not random noise. They are the fossilized imprints of the universe's very first structures, the quantum seeds from which everything we see today would eventually grow. In that subtle pattern of hot and cold, we hold the blueprint for the cosmos. Each fluctuation represents a region of the primordial plasma that was ever so slightly denser or less dense than its surroundings. Gravity is an amplifier of inequality. Over the eons that followed, those slightly denser patches pulled in more matter, growing under their own weight, while the less dense regions emptied out. The delicate ripples we see in the infant universe are the direct ancestors of galaxies, clusters, and the vast cosmic web that spans the heavens today. By decoding this map, cosmologists perform a kind of archaeology at the edge of time itself. The precise size and distribution of these temperature spots tell a detailed story about the universe's geometry. Is space flat like a sheet of paper or curved like the surface of a sphere? The pattern of the anisotropies provides the answer, confirming that on the largest scales, the geometry of our universe is flat to a remarkable degree. This map also reveals the universe's recipe. By analyzing how matter and radiation interacted in that early plasma, scientists can calculate with stunning accuracy the exact amounts of ordinary matter, dark matter, and dark energy that make up our cosmos. It is as if the first light carried a hidden message, a cosmic inventory etched into its very fabric, waiting 13.8 billion years to be read. This makes the surface of last scattering far more than a barrier. It is a snapshot of the universe at a single, pivotal moment of transition, from opaque to transparent, and it contains within its subtle imperfections the complete set of initial conditions for everything that came after. We are not just looking at a wall of light. We are reading the opening chapter of our own cosmic story, written in the language of temperature and density, a prologue imprinted on the sky for anyone with the patience and ingenuity to decipher it. These faint smudges of infrared light are time capsules from the cosmic dawn. The James Webb Space Telescope is not simply taking pretty pictures of distant galaxies. It is performing an act of profound archaeology, capturing photons that have journeyed for over 13 billion years, emitted when the universe was a mere infant of a few 100 million years old. These are not the majestic, structured spirals we see in our local universe. They are the chaotic, blobby, and intensely active nurseries of the very first stars, objects that existed at the absolute frontier of what our technology can resolve as discrete cosmic objects. Each one is a messenger from the end of a profound era known as the Cosmic Dark Ages, after the glow of the Big Bang faded into the cosmic microwave background. The universe entered a long, quiet chapter. For millions of years, it was a vast, expanding sea of neutral hydrogen and helium gas, dark and featureless, with no sources of light. The first stars to ignite within these primordial clouds did not just bring light. They brought revolution. Known as population 3 stars, these firstborns are thought to have been monsters, hundreds of times more massive than our Sun, burning ferociously hot and blue, and dying in spectacular supernova explosions after only a few million years. Their violent lives and deaths seeded the surrounding gas with the first heavy elements, the carbon, oxygen, and iron that would later become the building blocks of planets and life. But their most profound impact was on the cosmos itself. Their intense ultraviolet radiation began to blast apart the neutral hydrogen atoms that filled all of space, stripping away electrons in a process called reionization. This epoch of reionization, which unfolded over several hundred million years, fundamentally changed the nature of the universe, transforming it from an opaque fog of neutral gas back into the transparent intergalactic medium we see today. The galaxy's Webb is detecting are the engines of this transformation. Their faint, redshifted light carries the chemical fingerprints of those first stellar generations and the telltale signs of energetic radiation carving out transparent bubbles in the hydrogen fog. By studying the size, shape, and composition of these infant galaxies, we are witnessing the moment the universe turned its lights on for good, ending the dark ages and setting the stage for the rich cosmic tapestry that would follow. This is the current, bleeding edge of our observational reach. Every new deep field image from Webb pushes this frontier back a little further, finding galaxies that are slightly smaller, slightly redder, and slightly closer in time to the Big Bang itself. We are mapping the shoreline of our observable universe in objects, watching as the tide of technology slowly recedes to reveal ever more ancient ground. The most distant galaxy is not a place you could ever visit. This is the core truth that redefines our entire relationship with the cosmos. The edge we speak of is a profound illusion, a trick of perspective born from the marriage of light and time. When you peer through a telescope at a galaxy 13 billion light-years away, you are not seeing a location in space as it exists today. You are witnessing an event that occurred 13 billion years in the past. The light arriving at your eye is a messenger from a younger universe, carrying a portrait of a galaxy as it was when that photon began its journey. The object itself, in the present moment, has been carried away by the expansion of space to a position nearly 46 billion light-years distant. The edge, therefore, is not a wall in the cosmos, it is a boundary in time. The cosmic microwave background is the ultimate expression of this principle. It is not a physical shell at some far-off coordinate. It is the flash from a specific moment, 380,000 years after the Big Bang, that we see in every direction we look. We are surrounded by this moment, encased within a temporal sphere of ancient light. Any notion of traveling to this horizon is fundamentally futile. Imagine setting out in a starship toward the source of that primordial glow. You would be chasing a ghost. The region of space that emitted the light you see is not there anymore in that same spot. It has been receding for billions of years, carried outward by the stretching fabric of the universe. You would be pursuing a memory, not a destination. This transforms the observable universe from a map of places into a history book of events. Every point of light is a chapter, and its distance tells us not how far away it is, but how long ago its story was written. The horizon is the first chapter, the opening sentence of cosmic history, and it surrounds us completely. we are not looking out at the edge of something. We are looking inward into the deep past from a present moment that is forever isolated from those ancient scenes by an unbridgeable expanse of expanding space and time. Our cosmic horizon is not just a limit to our sight, but a limit to our knowledge. The accelerating expansion of the universe guarantees that a vast portion of everything that exists is already, and forever will be, beyond our ability to learn about. This is the information horizon, a boundary more profound than mere distance. It tells us that some of the most fundamental questions we can ask about reality may have no answers we can ever access. We are like sailors on an island in an expanding ocean. We can see a certain distance before the curvature of the water hides the rest of the sea. But in our case, the ocean itself is growing, pushing the horizon farther away while simultaneously ensuring that distant shores we have never seen will never come into view. The light from those shores will never reach us. No signal, no data, no message can ever cross that divide. This means our entire understanding of the cosmos is built from a finite and shrinking sample of data, a local neighborhood in an unimaginably vast totality. We can develop theories about what lies beyond, about the global shape and content of the universe, but we can never test those theories with direct observation. They become matters of elegant mathematics and logical inference, forever trapped on the far side of a causal divide. This creates an absolute epistemological boundary, a limit to what we can know in principle. Is the universe infinite or merely enormously large? Are there other domains with different physical laws, as some multiverse theories suggest? From our island, we may never know. The evidence required to settle these grand questions is receding from us faster than any probe, any thought, any hope of discovery could ever pursue. We are left to map the cosmos from a single, fixed point, constructing a model of the whole from a fragment that grows more isolated with every passing moment. The universe is not just hiding its distant reaches, it is actively erasing them from our future. This invisible wall of light forces us to confront a question that has haunted humanity for millennia. Is the universe finite or is it infinite? Our observable bubble, for all its staggering scale, presents us with a paradox. We can only measure the part we can see, yet that measurement implies something about the whole. If the cosmic expansion continues forever, and if space is geometrically flat as our best data suggests, then the universe as a totality is most likely infinite. There is no boundary, no outer wall, just more space, more galaxies, stretching without end in every direction. In such a reality, our entire observable cosmos, that magnificent sphere of 46.5 billion light-years, becomes an infinitesimal sample, a single grain of sand on an endless beach. This idea carries a consequence so staggering it bends the mind. In a truly infinite universe with a finite number of ways to arrange particles, every possible configuration must repeat. Somewhere, at a distance so vast it defies comprehension, there exists another galaxy identical to our Milky Way. Orbiting a star identical to our Sun is a planet identical to Earth. And on that planet, there exists a version of you reading a version of this script. The cosmos would contain not just one of everything, but an infinite number of every possible variation. This is not science fiction, but a logical implication of infinity playing out within the laws of physics. Yet infinity is a concept our brains did not evolve to grasp. We are wired for the local, the finite, the things we can touch and see. The observable horizon acts as a shield, protecting us from the dizzying vertigo of a reality without end. It gives us a neighborhood, a home we can map and understand, even as it hints at a vastness that lies forever beyond the fence. But there is another possibility, equally profound. Perhaps the universe is finite but unbounded. Think of the surface of a sphere like our planet. You can walk forever in one direction and never find an edge, yet the total area is finite. If the cosmos is shaped in a similar, higher dimensional way, then it too has no boundary but a limited volume. Travel far enough in one direction, and you would eventually return to your starting point from the opposite side, having circumnavigated all of existence. In such a cosmos, our horizon is not a sample of an infinite whole, but a window into a closed yet still unimaginably vast system. Both possibilities, the infinite and the finite unbounded, remove the need for a literal edge. They tell us that the horizon we study is not the end of something. It is the limit of our local perspective, a lens through which we must grapple with concepts that challenge our very place in the order of things. Whether we live in a boundless ocean or a majestic, self-contained sphere, the message is the same. Our significance is not defined by occupying the center, for there is none. It is defined by our capacity to look out from our tiny island of knowledge and dare to ask what lies beyond the light. These cosmic questions cannot be answered by telescopes alone. When direct observation fails, we must build new worlds inside machines. Cosmologists now rely on a powerful digital oracle, the supercomputer simulation, to model the unseeable. Starting with our best theories of physics, from the violent spark of inflation to the quiet push of dark energy described by the lambda CDM model, scientists program the fundamental laws of the universe into lines of code. They set the initial conditions, a set of numbers representing the density, temperature, and composition of the cosmos in its first fraction of a second, and then press play. The simulation runs the clock forward, calculating how gravity pulls matter together, how gas cools to form stars, and how galaxies collide and merge over billions of virtual years. The result is not a prediction of a specific galaxy, but a statistical portrait of a cosmos. It generates a vast, synthetic universe, complete with its own virtual galaxies arranged in a cosmic web, and its own version of the cosmic microwave background, complete with subtle temperature ripples. The true power lies in the comparison. Researchers can then take this digital creation and ask, does it look like home? They compare the statistical properties of their simulated universe to the real data from our telescopes. How are the galaxies clustered? What is the precise pattern of hot and cold spots in the simulated microwave background versus the one we actually observe? If the virtual cosmos matches our reality, it suggests the initial conditions and physical laws programmed into the simulation might be correct. It is a form of cosmic detective work, using the observable universe as a fingerprint to identify the unseen forces that shaped it. This allows us to test ideas about what happened before the cosmic microwave background, or what the large-scale structure of the universe might be like beyond our horizon. We cannot see those realms, but we can ask our simulations to show us what they would look like if our theories are true, and then check if the part we can see fits the pattern. In this way, computation becomes a new kind of telescope, one that peers not through space, but through possibility, extending our vision beyond nature's built-in limits to explore the architecture of reality itself. These digital universes hint at a possibility more exotic than any star. Some of the most intriguing simulations explore what might have happened in that first fraction of a second after inflation, a time of unimaginable density. Under such extreme pressure, the fabric of space-time itself might have tied itself into knots, creating objects that are not made of matter as we know it, but from the pure geometry of gravity. These are the hypothesized primordial black holes. Unlike the stellar black holes formed from collapsing giant stars, these would be relics from the universe's very first moments. They are thought to have sprung into existence not from a dying sun, but from the intense gravitational collapse of ultra-dense regions in that seething early cosmos. Picture the infant universe not as a smooth soup, but as a turbulent, bubbling cauldron, where the density peaked in a particularly sharp spike, gravity could have won an instant victory, pinching off a pocket of space-time so severely that it formed a black hole. These objects could be almost any size, from smaller than an atom to many times the mass of our Sun, frozen fossils from a time before the first atoms even existed. Their potential existence transforms them from theoretical curiosities into the ultimate cosmic time capsules. If we could find one, it would be a direct messenger from an epoch forever hidden behind the wall of the cosmic microwave background, a tangible piece of the universe's first second. But how do you hunt for a fossil that emits no light and could be almost anywhere? The search relies on their ghostly gravitational influence. Astronomers look for subtle flickers in the light of distant stars, a telltale sign of an invisible, compact object, a primordial black hole passing in front and bending the starlight with its gravity, an effect called microlensing. They also scrutinize the earliest light we can see, the cosmic microwave background, for any imprints or distortions that vast numbers of these ancient objects might have left as they moved through the primordial plasma. Perhaps most profoundly, some primordial black holes could solve one of cosmology's greatest mysteries. If they exist in vast numbers at certain masses, they could constitute the invisible gravitational glue we call dark matter. This would mean the missing majority of matter in the cosmos is not a sea of unknown particles, but a population of ancient black holes, relics from the dawn of time silently holding galaxies together. Finding even one would be a window into physics at energies far beyond any particle collider, offering hard evidence from a realm we thought was forever lost to observation. They represent the tantalizing possibility that the edge of our vision is not empty, but dotted with silent, gravitational monuments to the universe's violent birth. Light itself does not experience the stretching of space. From the photon's timeless perspective, its journey from the Big Bang to our telescope is instantaneous. This reveals a profound disconnect between how we measure the cosmos and how light actually traverses it. To bridge this gap, physicists use a clever mathematical tool called conformal time. It is not a new kind of clock, but a rescaling of our ordinary cosmic time that factors out the relentless expansion of the universe. Think of it as drawing a map of a hiking trail. An ordinary map shows the winding, uphill path you must walk, accounting for every contour. A conformal time map, however, flattens all those contours, showing the trail as a straight line of pure distance. In this transformed framework, the complicated, stretching history of the cosmos is smoothed out. The expansion that has been carrying galaxies apart is mathematically removed from the equation. What remains is a simplified, static stage where light, at last, travels in perfectly straight lines. This perspective offers a crystal-clear view of our cosmic horizon. In conformal time, the Big Bang is not an expanding fireball, but a single point in the past. From that point, light has had a finite amount of this rescaled time to travel outward. Our particle horizon, that ultimate limit of what we can see, becomes elegantly simple. It is nothing more than the distance light has traveled in conformal time since the beginning. There is no stretching fabric to complicate the journey, no accelerating finish line. It is simply the farthest any signal could have possibly reached us in this flattened version of history. This reframes the edge of the observable universe in a deeply illuminating way. That galaxy whose light we see today is not 46 billion light-years away in some abstract, expanding sense. In the framework of conformal time, it is precisely as far from us as light could have traveled since the universe began. The horizon is not a place out there that light is desperately rushing toward. It is the boundary of all past events whose signals, traveling on those straightened paths, are only just now completing their epic journey to our eyes. This clarifies the true causal structure of the cosmos. Everything within our conformal horizon is an event that could have influenced us because its light has had time to arrive. Everything beyond it is causally disconnected, separated from us by a gulf that not even light on its straightened path could cross in the age of the universe. Conformal time strips away the complication of expansion to reveal a simpler, more fundamental truth. Our visible cosmos is not defined by the swelling of space, but by the immutable speed of light and the finite age of reality. The edge is not a wall in the growing universe. It is the final echo from the first moment, finally reaching us after traversing a timeless, flattened void. That distant wall of light is slowly fading from view. The cosmic microwave background, our most precious relic from the dawn of time, is not a permanent feature of the cosmos. As the expansion of the universe continues to accelerate, every photon of that ancient afterglow is being stretched to longer and longer wavelengths. Over trillions of years, that faint microwave hum will redshift first into the radio band, and then its signal will become so diluted, so spread across the expanding void, that it will fade into utter undetectability. The universe's baby picture will be erased by the relentless passage of time. This is not the only loss future observers will face. One by one, the galaxies we see today will cross the cosmic event horizon and vanish, their final photons arriving as an infinitely dim farewell. A civilization arising in the distant future, perhaps 100 billion years from now, will gaze upon a profoundly different sky. It will be a dark and nearly empty expanse, containing only the merged stars of their own local galactic group. The brilliant tapestry of billions of galaxies, the direct evidence of an expanding universe and a hot beginning, will have receded forever beyond the reach of their science. They will have no direct evidence of the Big Bang, no map of the cosmic microwave background, and no view of the earliest galaxies. The universe will present itself as a static, island-filled void, with no obvious clues to its explosive origin or its accelerating fate. How, then, could such a civilization ever piece together the true history of the cosmos? They would become cosmic detectives, searching for fossilized clues in the only ancient artifacts left to them. They might study the chemical composition of the oldest surviving stars in their galaxy. These ancient suns, forged from the nearly pure hydrogen and helium of the early universe, contain trace amounts of heavier elements forged in the first generations of massive stars. By decoding this chemical fingerprint, they could infer that a period of intense stellar birth and death must have occurred long before their own star formed. They might also analyze the precise motions of galaxies within their bound local group, looking for subtle dynamical evidence of an earlier, denser state. But these would be indirect, circumstantial pieces of evidence, a far cry from the direct observational proof we enjoy today. This realization grants our current era a profound and fleeting privilege. We are living in the cosmic golden hour, a narrow window in the multi-trillion-year lifespan of the universe when the afterglow of creation is still visible, and the story of the cosmic dawn is written clearly across the sky. We are the first generation of true cosmic archaeologists, equipped with tools to dig directly into the strata of time itself. Our mission, therefore, transcends pure curiosity. We are tasked with decoding and preserving the origin story of everything, not just for ourselves, but for all potential minds that will come after, in epochs of profound cosmological blindness. The knowledge we gather now may become the foundational myth, the sacred text, of civilizations that will know the universe only as a quiet, dark, and seemingly eternal home. The true limit of our vision is not a place but a story. It is a narrative written in the language of redshifted light and stretching space, a tale that begins with a brilliant flash and ends in a silent, accelerating dark. Our journey to the edge has shown us that the cosmos is not a static museum, but a living, breathing entity with a past we can see, a present we inhabit, and a future we can only infer. That staggering bubble, 46.5 billion light-years in radius, is not a boundary of creation. It is the boundary of our connection to it, a horizon built from the finite speed of light, the relentless expansion of space, and the simple, profound fact that the universe has a finite age. Within that bubble, we have decoded the oldest page of the cosmic story, the cosmic microwave background, and traced the lineage of galaxies back to their first, faint glimmers. We have confronted the forces that both reveal and conceal, from the primordial opacity that hides the universe's infancy to the dark energy that is slowly drawing a veil over its maturity. Yet, in the face of these fundamental limits, human curiosity refuses to be confined. We are building new senses, learning to listen to the ripples in space-time, and dreaming of one day catching the ghosts of the first second. This quest redefines the very act of looking up. Every star, every galaxy, every faint smudge of light in the void is not just an object in space. It is a chapter in a history book, a message from a specific moment in the deep past, arriving at your eyes on a beam of light that has traveled across epochs. You are, in the most literal sense, a time traveler surrounded by the echoes of cosmic events. The edge of the observable universe is not out there. It is all around you, and it is receding with every passing moment, carrying with it the untold stories of realms we will never know. So the next time you find yourself under a clear night sky, remember this. You are standing at the center of your own magnificent story, looking out to the very edge of time itself, connected to the dawn of everything by the ancient light now falling on your face. If this voyage to the frontier has reshaped your view of the cosmos, share what you believe lies beyond our horizon in the comments below. For more journeys to the edges of understanding, be sure to subscribe.